People have been saying various things during the break that remind me that I should have been more clear about various items. So let me try to clarify those things. In this problem, we're going to have an MCMC data set with a column for mu and a column for tau, because that's how WinBugs is working with scale, and a column for nu. And this is going to be the monitoring runs, the monitoring iterations from 1 to little m of those. I haven't said yet how long to do a burn-in for and how long to monitor for. We'll get to that later. Remember, in order to, strictly speaking, calculate something like the marginal posterior mean for mu, which is written as the conditional expectation of mu given the data vector and the background information. To calculate that, first what I would have to do is I would have to work out the marginal posterior. If I were trying to do it analytically, I'd have to work out the marginal posterior for mu given the data and the background. And you remember the way I have to do that is I'd have to do a double integral over the joint posterior for all three things, mu and tau and nu, given y and beta, and I have to integrate over d tau and d nu. That gets me the marginal posterior for mu. And then to get this expectation, I'd have to integrate mu times that to get the posterior mean. Mu given the data, d mu. So that's the math of what we would need to get for the posterior mean. It involves, first of all, a double integral to work out the marginal posterior, and then a single integral to actually find out what the mean is. How do we avoid all those integrations in MCMC? Well, what's my estimate of the posterior mean in MCMC? What do we agree? If these things are valid, identically distributed draws from the posterior distribution, which they are by the construction of the Metropolis-Hastings algorithm, and they're stationary draws. They're draws from the stationary distribution, which is supposed to be the posterior I'm interested in, and that's all been taken care of for us by WinBugs. Then what did we say in using the MCMC data set? What did we say we had to do to get an estimate of the posterior mean? Just take the sample mean. So first of all, if you want to know something about mu in the MCMC way of looking at things, instead of having to do the double integral that marginalizes to get rid of the other things, here's the version of marginalization in MCMC. You take a sheet of paper and you cover over the rest of the MCMC data set, and you look only in that column. You have just marginalized. There it is. That's how that gets done. So no integrals necessary to work out marginal distributions. You simply ignore all the other columns in the MCMC data set. Then here's another integral here. We're approximating that integral with Monte Carlo integration. We're saying that a sample mean is like what you'd get by taking an exact mean. And so Monte Carlo integration from taking a sample mean approximates for that integral there. So all problems having to do with marginalization disappear just by ignoring the other columns. Means, standard deviations, whatever you want, they would all involve integrals. Also, they're all just basically Monte Carlo integration by taking samples. Now, suppose there's some quantity that's a function of one of these parameters. In fact, I defined one in that WinBugs program and didn't tell you why this worked. I have a quantity called sigma, which is 1 over the square root of tau, and that's a deterministic function of the unknown thing. Oops, I meant to write tau. Then what can I do in the world of MCMC to get an exact and correct posterior distribution for sigma? If I have an exact and correct marginal posterior distribution for tau, I simply compute for each row in the MCMC data set, whatever tau was here, maybe tau was 0.27 here, I just calculate 1 over the square root of 0.27 over here and put it in. And having drawn correctly, simulated correctly from the marginal for tau, this must be a correct simulation for the marginal of sigma. So once again, If I tried to do this with math, there would have been, I'd have to write down a transformation that involved, remember that was that stuff about two different transformations in the Jacobian and integrating once to get the normalizing constant, integrating out to get the marginal. I mean, it was just a mess, right? All that stuff goes away. You just take any function of the data that you want and simply use it as another column to be monitored in the MCMC data set, and you're done. So all those integrals go away as well. Now the last integral that arose, the next to last one was the normalizing constant, but we've already agreed that one disappears because we don't even need to normalize the posterior distribution. The posterior distribution we're sampling from, because it appears in the Metropolis-Hastings ratio only as an unnormalized version of itself. So that integral goes away. The very last integral that arises is in the predictive distribution. So let me remind you how that went. What's the predictive distribution for the next observation, having seen the first n observations? So y right there is y1 through yn, as usual. Well, we went through this repeatedly. We say to ourselves, and remembering that in this problem theta is the vector mu, tau, nu, we say to ourselves, I'm having a hard time thinking about this thing here, but it would sure start to get a lot easier if I brought in theta. And so I bring in theta as follows. I use the law of total probability to write down that it's the joint distribution of yn plus 1 and theta, given y and b, added up over all the theta values. So that's actually in disguise a triple integral across all the elements of theta. Then I say to myself, well, this doesn't look much fun either, because I'd rather that theta be on the other side of the conditioning bar, because if it's over there, then I can start talking about how yn plus 1 should behave if I knew what theta was. So I simply take and I force the theta to be over on the other side of the conditioning bar where I want it to be, and then I work out by the definition of conditional probability what I have to multiply by to get that to be a correct equation, and the answer turns out to be, naturally enough, the posterior distribution for y, or rather for theta given the data so far. And then I make that crucial move in which I say, if I'm asking you to predict the next observation, and I offer you both the truth about the parameter vector and all the data values previously, you notice that you don't need the data values. In the presence of the truth, you can go just with the truth. And so I cancel that, and this now becomes the sampling distribution for a new y times the posterior distribution given the data so far. So if I were trying to calculate this quantity directly, I would have to evaluate that triple integral, and it wouldn't be any fun. But suppose I wanted to simulate from this distribution instead. Look at the form of this. This is a mixture representation. Look, it's a weighted average of this weighted by that. And so you're using that fact we talked about before, where you can either model something unknown to you, y, hierarchically, or you can model, directly, or you can model it hierarchically by first going x and then y given x. The analog of that here is you could either model yn plus 1 directly, or you could first model, actually let me write it more carefully. You could either try to model yn plus 1 given y and b directly, or if you couldn't figure out how to do that, you could model it hierarchically by first modeling yn plus 1 given theta and b, and then modeling, let me try to, no, I'm sorry. First, what you would do is you would model theta given y and b, and then you would model yn plus 1 given theta, y, and b. And we saw that the theta cancels. I mean, rather the y cancels. So check that out. If you want a sample from this predictive distribution, what it says to do is what? First, make a draw from what distribution? The posterior. And then make a draw from the sampling distribution of the next observation using the theta that you got from the posterior. So that's what this mixture representation says to do. To sample from the predictive, you just first take a draw from the posterior, and then you take a draw from the sampling distribution for the new data given that particular value of theta. But look, that's ideally suited for the MCMC data set. I can just create a new value here called y new, my next observation. And look, what do I have to do to simulate it? take a draw from the posterior, but look, there it is right there. There's a draw from the posterior. It's sitting right there. And now make a draw from the sampling distribution for the next observation given that particular draw. And there you have it. There you have a draw from the predictive and another draw from the predictive and so on. And moreover, because you're taking these guys here one by one, and they're going to be correlated with each other in time series sense, but you're now conditioning on them and making draws from the t distribution with those vectors. This column here in the MCMC data set is going to actually be IID. So you're going to learn about the predictive distribution even faster than you learn about the other parameters. So every integration that a Bayesian ever would need to make can be bypassed completely, can be sidestepped by this fantastic idea of sampling from the posterior distribution and then doing appropriate things with the samples. It's a lightning bolt. It made possible once the Bayesian community finally, the penny dropped and they finally noticed that it was out there from about 1990 forward over the past 20 some years. It's made possible an absolute explosion in the practical use of Bayesian methods in real problems. So now I think you can see the reason for this syntax is it says to WinBugs, create a new node in the graph, please. That's a deterministic function of the tau node, and sample it in each row of the MCMC data set. So it becomes a new column in the MCMC data set. Similarly, look, this says to do just what we said. Take a draw from mu, tau, and nu, and then use those values for mu, tau, and nu, and make a draw from the t distribution with those values. That's why this symbol is right there. It says is distributed as. It says make a draw from the t distribution using the values of mu, tau, and nu in the particular row in the MCMC data set that you've got. So this syntax automatically samples from the predictive. Fantastic.
You're just ordering it in that order.
I happen to put it in that order.
It's nice for you, but it doesn't know.
No. I could have.
The DAG
The DAG works out what's going on here, and I could have written what I call parts 1, 2, and 3 of this. I could have written them down in any order inside this file, and it would have been just as good as any other order. It would not be a good idea to take stuff that does not involve the for loop and stuff it inside the for loop. That would probably confuse WinBugs. But beyond that, you can do any damn thing you want with this stuff, and it's probably going to be fine. Yes, it knows that what you're doing right here is you're defining the sampling distribution. Literally, it's saying the y sub i's given mu, tau, and nu are conditionally IID from the t distribution with those parameters as I runs from 1 to n. So that's like our marginal sampling distribution for each observation. And because they're conditionally IID, the joint sampling distribution is the product of the marginals. It comes directly out of that for loop. And that joint distribution, when re-expressed as a function of mu, tau, and nu, is the likelihood function. So it's got everything it needs. It's right. It's cool. It's right there in that syntax. Yeah, it's cool. Y is a deterministic node in the graph because it's been given data values over here. So when WinBugs compiles these 3 files together, it will notice that Y is the deterministic node that has been determined over here. It will notice that N is a deterministic node in the graph that has been determined over here through the data set. And it will work out by syntax that mu and tau and nu are stochastic nodes because they're next to tilde signs. Also y dot nu is. And that sigma is the deterministic node that's driven by a stochastic node. So it can work all that out from the syntax directly. We don't have to hold its hand any more than that. All right, so here we go. We're going to fit our first model. I pull down and use the model specification tool. And I should tell you that all of this stuff is in this file. So if you go well forward here into the bottom part, I have screenshots of what everything looks like at various steps. And below that, I have text underneath that tells you what to do to get all this stuff done. So if you want to practice with this yourself, start on page 72 of this handout, and all the steps are right there. So showing you in real time, I bring down the specification tool from the little model pull-down menu, and it says it wants to try to check the model. You can see how that little click there is highlighted, and the rest of them are not ready to use. So I go over and I foreground the model file, and I come back and click on check model. and it says the much to be desired message model is syntactically correct. When you do this yourself, you will not get that message at first. Let me show you the kind of thing that can go wrong. Let me go back in here and deliberately start screwing it up. So I'm putting another parenthesis right there. We know that's a syntax error, right? I'll go back and click on this again and hit check model. And at first it warns me that the new model will replace the old one. That's a good warning. And then it says invalid or unexpected token scanned, and it beeps. And look, it put the cursor right where the problem was. So that's pretty good, right? So you can look right there and see, you know what the problem was. All right, so it's got a primitive debugging capability within it, and also the manual helps with stuff like that. So here is my model, and I check it, and it's syntactically correct. Iterate until you get that message, please. Then foreground the data window and click load data, and you will get the second much to be desired message, data loaded. Again, if I'd made a syntax error in this thing, it would have warned me about it, for example. Now that the data have been loaded and the model has been checked, I'm now ready to hit the compile button, and I do so. I hit compile, and I get the much to be desired message, model compiled. Now all that remains is to tell it about the initial values, and so I foreground the initial values file, and I hit load inits. And it says, this chain contains uninitialized variables, meaning that it's not ready to actually do business for us yet because I haven't initialized everything that needed initializing. So I look back and I see that must mean that there are one or more stochastic nodes in the graph that have not been initialized in my initial values file. Can anybody see what they are or what it is? Yeah, I should have, to make it completely above board, I should have initialized y.new also. But having given it good parameter values for mu and tau and nu as initial values, I can be lazy at this point, and I can just hit the generate initial values button, and it will take simulated draws from the distributions that are specified by everything it knows so far. So I click the gen inits button, and I get the absolutely A+ message that I've been waiting for out of WinBugs. Initial values generated, comma, model initialized. You are really waiting for it to say to you model initialized, because at that point, it's ready to go. It's ready to sample. And all the syntax errors are gone now. It's all ready. So at this point, I kill the specification tool because it's no longer of any use. And I go up to the model pull-down menu again, and I choose update this time. And now this introduces us to the update tool. And the update tool has the following elements. You tell it how many updates you want in that little window there. It always defaults to 1,000 at the beginning because it knows you're going to make a burn-in now. And it thinks that you need a default burn-in length of 1,000 iterations. This number was not chosen by careful thought. They just put a number in that window and made it default. I'll say more about that in a minute. The refresh window tells you how often it's going to tell you how many updates it's finished so far as a function of the number you put over here. So if you leave a refresh 100, it will show you the updates in blocks of 100. It will say I've finished 100, 200, 300, and so on. If you're trying to get 500,000 iterations and the updating is really quick, you don't want the refresh thing to be at 100 because it's going to spend a lot of CPU time writing to that little window over and over again, telling you that it's finished another 100 updates, it's finished another 100 updates. So usually to make things run faster, you change the refresh window to a bigger number than that. Later, I'm going to update the number in the update tool to 100,000 to get my monitoring run. And at that point, I would want to refresh at least every 1,000, make it at least 1,000 to keep it from wasting its time. Maybe even make it 10,000 to keep it from wasting its time. But at the moment, I'm going to leave it at 1,000. Look, it has a window in which I can tell it how often to thin, like I told you before. If you leave it at 1, it doesn't do any thinning. It thins by 1, which is like not thinning. Here, it'll tell you how many iterations it's finished so far. And then there's this thing about overlaps and adapting. Those are technical things about how WinBugs does the proposal distributions, and I won't talk about them. Except to say that the idea that was used to implement the adapting part, Spiegelhalter stole from Bill Brown and me. Back in those days when we were all working in England, Bill and I would go over to Cambridge and talk to the WinBugs team about what we've been doing, and they would come over to us sometimes and talk about what they'd been doing. And at one point we said to them, we've put this adaptive MCMC stuff into our story, And Spiegelhalter said, "Oh, that looks like a good idea. I'm going to steal that from you," and he did. So, and the adapting window being checked means that it has worked out that it needs to use a version of slice sampling in which it has to do something like choosing the proposal distribution standard deviations based on how the data is, rather than using them in a fixed sort of way. So, what it's going to do now, without telling you, is it's going to use the first 500 of the next 1,000 iterations to do an adaptation period, and that will leave you with a burn-in of only 500. And so if you didn't know what's going on, you would have thought you just got a burn-in of 1,000, but actually what you got was a burn-in of 500 after the adaptation period. Now, I will actually warrant for you that the distribution, the Markov chain, is already in equilibrium with these starting values. Either already in equilibrium or essentially in equilibrium. And yet, most people go ahead and do a kind of a superstitious update, burn-in anyway. And I'll do that here, and you'll see how fast it goes. And so this is going to correspond, as I said, with the adapting box check to an adaptation period of 500 followed by a burn-in of 500. Now watch how fast it goes. It's gone. So if you burn in and you were already in equilibrium, does it hurt anything? Can you stray away from equilibrium by burning in too long? No. Equilibrium is an absorbing state. Once you're there, you never leave it. So burning in more than you need to just wastes clock time and CPU time, but it doesn't do anything wrong. Not burning in long enough, on the other hand, can give trouble, right? Because then you will claim that in the monitoring part, you're actually sampling from the equilibrium distribution and you're not there yet. Here is a simple graphical way to discover whether you have reached equilibrium. Get WinBugs to show you the actual trace all the way from iteration 0 of what the theta star t looks like. And if it looks like the following, if you give it a really awful starting value and there's a high degree of autocorrelation, what it'll look like is this. Suppose the true distribution is up here, the true marginal for theta is up here. Then what it'll do is it'll look like this. And then once it gets here, it'll just settle in and mess about. And wouldn't you agree that's a pretty dead giveaway about how long the burn-in period needs to be? You burn in until about there, and you throw that away and call it good, right? If I had done that a minute ago, there's a way I'll show you in a minute for actually watching the movie for the updates to occur. If I'd done that a minute ago, it would have already said, it would have already looked like this. It would have already said, in effect, I'm in equilibrium, so don't mess with me. You know, I'm fine. But if you're in a situation where you need a burn-in, that's a good way to visually see how long the burn-in needs to be. I just said any old parameter of interest, if that's what monitoring its time series looks like, starting from iteration 0, then you could tell if this was iteration 1600, you could tell that you should throw away the first 1600 and monitor from there. Oh, yes, you do. You have to check them all. But in fact, in this problem, I'm going to tell you that you don't have to check any of them because we're already in equilibrium. This problem is so easy. The posterior distribution here is strongly unimodal, and nothing bad can happen. I mean, we're there. No worries. So I've now done my burn-in period, and the way I know that was a burn-in period rather than a monitoring period is that I haven't told WinBugs yet to monitor anything. So now, after having updated for 1,000 iterations, 500 of which were burn-in, I now go to the inference. Pardon? Oh yes, thank you. I now go to the inference pull-down menu, and I choose samples, and I get the thing called the sample monitor tool. And now it wants to know which nodes in the graph I would like to monitor. And so I say to myself, well, okay, I sure want to know about mu. And as soon as you type in mu, before that, the little set button was not settable. But now, typing in a valid node in the graph, it becomes settable, and I click on it and set it. Now I want to monitor tau and set. And I want to monitor nu and set. If I tried to monitor y, what would happen? it doesn't change. And so I can tell it in the monitor tool that I want to monitor Y, and then when it comes down to the end and tells me what I've monitored, Y will not be there. It says, you asked me for something stupid. You asked me to monitor the data, and the data doesn't move around. Same thing if I tried to monitor N. If I tried to monitor I, it probably won't even work, right? Yeah, I is not a real node in the graph. It's just a looping variable. But I could monitor N if I want, and again, it would basically say, okay, you can tell me you want to monitor it, but I won't give you any monitoring results because it's static. But then I am interested in sigma also, so I'll monitor that as well, and I am interested in y.new as well, so I'll monitor that as well. All right, now we're ready to do the actual monitoring. And so I'm going to go back over here and do 100,000 updates in the monitoring phase and refresh every 10,000. And let's go to the races. And now you can see it manages to do 10,000 iterations about the rate of 1 every 2 seconds for 10,000 iterations. So this isn't too shabby. It took 14 seconds to get 100,000 iterations. Not too bad. Not even time to get a cup of coffee. This particular box here is something called a portable workstation. I don't buy laptops very often. I use them until they die and then get another one. And so my last laptop was 10 years old. And I'm probably not going to buy a new laptop every year this way either. So I decided to go ahead and buy a really good laptop and use it until it dies. So this thing has 8 CPUs in it, and it has an amazing amount of RAM, a lot of which is that kind of really, really, really fast RAM and all the huge disks and so on. I believe that WinBugs doesn't know anything about that at all. It's running in 64-bit, but I think it only runs on 1 CPU at a time. And so all that extra power I got in there, it's not doing me any good at all. The only program I know that I've currently bought that uses all 8 CPUs is this program here called Deep Fritz. It plays chess, and it's set up to find out how many CPUs there are and use them all. And so that makes it a lot harder opponent to beat, right? Because it's using all 8 CPUs against you. But there you go. All right, now we're actually ready to do the fun part, which is to see what we just learned about the Pasteur distribution. So I'm going to minimize the model window, and I'm going to minimize the data window, and minimize the initial values window in order to have more room on the screen here. And I'm going to put the monitor tool down here at the bottom and the update tool down here at the bottom. And now I'm going to start looking at stuff. So there's our 5 nodes that we asked to monitor. And so let's look at them. So here's mu, and there's all this stuff I can do. Yes, please? Pardon? I'm going to defer that question because I don't know enough about how to do it to show you how to do it now without making a fool of myself. So I'm going to make a note that that's a question you want answered, and I'll do that. I'll try to do that for you for next time. I may be wrong about that. Maybe what happens is if you specify the DAG, you can then press a button and it will show you what the algebraic model is. And maybe it doesn't go the other way, but I'm going to find out about that for you for next time. All right, so there's a button called Trace, and look what it does. It shows the dynamic trace of how the sampling actually occurred over the most recent iterations. And for some reason, there's a flaw in their code. It's not providing us with the actual iteration numbers, but I can tell you that's about the last 1,000 iterations or maybe the last 500 iterations. If you want to look at the entire history of all the sampling across the 100,000 iterations, you hit the history button, and it gives you the following. At this level of granularity, looking at the iterations, does that look like it's sampling from a stationary distribution? Yeah, it's not trending upward or downward. It's not having violent periods where there's greater variability than others, and so on. It just looks like a nice sample from an equilibrium distribution. But it's hard to say because everything's been jammed into the entire 100,000 iterations in one picture. The marginal Pasteur for mu, well, there it is. You just hit the density button. That's my marginal Pasteur for mu. Numerical summaries of that Pasteur, I simply hit the stats button, and it usually defaults to, again, a type size that's a little too small, so I go up to attributes and tell it to print that out, let's say in 10 points, so I can see things a little better. Yeah, I guess that's okay. And now I begin to look at the numbers. So the posterior mean, without doing any integrations, is 404.3 with this data set. The posterior standard deviation is about 0.47. The Monte Carlo error of the posterior mean is about 0.002. And so 100,000 iterations has been very, very ample to get at least 4 significant figures in mu, and probably quite a few more than that. I could certainly have the next figure if I wanted it, and almost the next one after that. But that's pedantic, right? It's more significance than you actually need. The numbers themselves were only to 3 significant figures, and so I'm not going to push that. It tells me what the posterior median is, and it tells me what the posterior 2.5% and 97.5% points are, so that I can write down the equal tails, the 95% equal tails posterior inferential interval about mu. In other words, on the basis of this model, with this data set and diffuse prior information, I think that NB10 weighs about 404.3 micrograms below the nominal weight of 10 grams, give or take about 0.47 micrograms, and my 95% interval for it runs from 403.4 up to 405.2. So we have completely solved the inferential problem using a method that does not require any integrations. That's the beauty of this technique. There's a button called Coda now. If I click on that, I'll get 2 files right away. One of them is an indexing file that tells you what you're about to see in the other file. And so it tells you this is the variable mu, and you've gotten information from iteration 1 to 100,000 after the burn-in period started and things actually began. But it remembers that you started with iteration number 1 all the way up to 1,000 earlier. And so it calls that first monitoring iteration 1001. And what it gives you in this file is it gives you all the actual data values next to the iterations that they were arrived at. There's some place inside here that you can ask for more significant figures, but I don't remember how to do that. And so the purpose of having this is that if you wanted to dump out these samples from the posterior distribution into a file and analyze them in R or some other place, this is an easy thing to do. I just go up here now, foreground this file, and choose File, Save As, and now I'm going to have a text file. Look, it says it wants to save it in a format called .odc, which is this weird internal format that only it knows about. So I would definitely say, no, please don't do that. Choose instead plain text as the nature in which this is going to be written out. And then I save it, and then I can read it into R and mess with it in any way I want. In particular, if you don't like the MCMC diagnostics that are here inside WinBugs, you can pass these on to a big ensemble of MCMC diagnostics that's available in R. So I'm going to go ahead and kill that window off and kill this window off as well. Now, the next button gives me something called running quantiles, and this is a moderately useful picture. What it tells me is, it says, if I had stopped after only 5,000 monitoring iterations, what did I think the 95% interval looked like? If instead I'd stopped at 25,000 iterations, monitoring iterations, what do I think the 95% interval would have looked like? And so on, all the way through all the different places. Wow, where did it go? Wow, let's do that. Oh, it's here, okay. And so, does this picture look to you as though we seem to be sampling from a stationary distribution? Yes, that's what this picture is trying to tell you. If those intervals were on the move, if they got wider or narrower, I guess after a while they'd have to get narrower, but if they got narrower over time, you would know that you weren't sampling originally from the equilibrium distribution, and you'd want to go back and throw some more iterations away as burn-in. No, I don't want to save those changes. Then there's something called the BGR diagnostics, and GR part stands for Gelman and Rubin, 2 people who wrote about a particular kind of diagnostic. I don't remember who the B stands for, but it only applies to the case where you were suspicious that there might be multiple modes and that you had already run multiple chains. Because something I didn't mention to you before is that in the sample monitor tool, there's a window here called chains, from chain 1 to chain 1 here. I could have asked it to run 4 or 5 separate chains with different starting values and save them all inside WinBugs. And then this BGR diagnostic does an analysis of variance to see how much variability there is between the output of the chains and how much variability there is within them, and then it decides whether the chains differ from each other by enough that you should be worried about multimodality. I'm not going to do that here, but let's look at the autocorrelation. This is the thing that I called before, the autocorrelation function for the parameter mu when thought of as a time series. It always has a trivial spike up to 1.0 at lag 0, and then it trails off from there. And you can see that by the time we get to lag 1, 2, 3, 4, it's already gone down to white noise. And so this is an example of a slightly correlated a time series, but not too bad. All of these spikes are positive, so we do have a little bit of positive autocorrelation. The first order autocorrelation is only about what? Only about 0.3. So the parameter mu is mixing very nicely. That's what this shows. All right, I'll kill that off, and I'll go back and get some more stuff about the other parameters. Basically, we know about the inference parameter already. We've gotten what we want. I can show you actually something a little bit more. If we wanted to go ahead and get some more updates, I should have shown you this before, actually. Let's go ahead and get the one for new and hit trace. I'll talk about that picture in a minute, which, as you can see, looks very different from the one for new. And let's look at sigma and put on the trace. At the cost of taking a fair amount of CPU time to do this, WinBugs can present for you a movie. And so now watch. I tell it I want another 1,000 updates, and I want to refresh every 10 iterations. And I hit update, and now watch. It actually shows you the movie of the MCMC sampling occurring in real time. And you can look and see, does it look like it's mixing okay based upon how the movie went. And so it's kind of cool. It used up a lot of CPU time to do that because it wouldn't have taken ordinarily anywhere near that long to get those. It took 6 seconds to do 1,000 updates, whereas before it took 14 seconds to do 100,000 updates. So a lot of that CPU time was spent in showing you this movie. But if you want to watch the movie, there it is. So, okay. Now let's look at sigma. Its history looks like this. And it looks pretty nice too, like it's mixing just fine. Well, it's funny. WinBugs has funny default ideas of how to draw the vertical scale. It's decided to go all the way up to 8.0 because there was one number that was bigger than 6.0. So actually, it really only needed to draw it up to about 6.25. And anyway, the reason that this is so spread out is that it's a scale parameter, and we only have 100 observations, and so we haven't actually pinned its value down very well yet. It has a long right-hand tail in its marginal posterior, as you'd expect from a scale parameter. And the stats on it look like this. We believe on the basis of this analysis that if this model is correct, using the prior information that I used, the posterior standard deviation of the scale parameter in this T model is about 3.86, give or take about 0.44. Again, the Monte Carlo error is on the order of 0.003. I should say that strictly speaking, this is the right Monte Carlo error only for the mean, but all of the other ones have Monte Carlo errors that are about the same order of magnitude as all the other things mentioned here as the mean. So you can think of that as an approximate Monte Carlo error for all of the different elements here. And you can see the posterior median is a little different from the mean, illustrating the skewness. And we would think that back in the population that it's okay to generalize to the inferential interval runs from about 3 up to about 4.8. Now let's check out its quantile plot. It's also mixing very nicely. And let's check out its autocorrelation. It's mixing less well. It looks like an autoregressive time series of order 1. I'll show you what that means later on. With the first order autocorrelation of about plus 0.6. So it's mixing worse than the mu parameter. But still, we've already, with 100,000 draws, we've got a Monte Carlo standard error that's down there about 0.003. How much more accuracy do you want? So even though it's mixing badly, it only took 14 seconds to get quite a lot of significant figures. So what do we got? Can we report the 3 in 3.861? Yes. Can we report the 3.8? Yes. Can we report the 3.86? Yes. Can we report the 3.861? No, because the 1 is noisy. See how the Monte Carlo error is on the order of 0.003, and if we reported 3.861, we would be overstating what we know on the basis of 100,000 draws. So that's how you use the Monte Carlo error to see how much you know. Okay, now let's look at, if we look at tau, tau is that deterministic function of sigma. It's not very interesting. Its density sort of looks like some other thing that's sort of like a scale parameter. And its autocorrelation plot, of course, has to be identical to the one from sigma because they're deterministic functions of each other. The most interesting parameter is the degrees of freedom parameter nu, whose trace, would you say that time series is blocky or sticky or behaving well? It's way not blocky, right? I call that sticky. It's not moving very much each time. And you can see from the marginal time trace for it that it's definitely got a strong long right-hand tail, and it keeps bumping up against that 2.0 boundary at the bottom. For people who aren't so dogmatic about infinite variances as I am, you could have tried going back and using a uniform distribution that goes down below 2 and see how much support the T model has for that, and you would find, I've done it before, you'd find that it would go ahead and go down to around 2, 1.5, 1.0. It'll let you go wherever you let it go. Okay, now the posterior for the degrees of freedom parameter with that uniform prior I used is sharply skewed. It has a long right-hand tail. It has a mode at about hard to tell from because the mode is not actually printed here, but it appears to have a mode right about 3 degrees of freedom. The mean degrees of freedom is about 3.6, and the standard error connected with that, or posterior standard deviation connected with that, is about 1.17. And our interval runs from about 2 to about 6.5 degrees of freedom. The main thing to notice is that the Monte Carlo error here is vastly larger than it was for all the other things we've looked at so far. We were getting numbers like 0.003 for the other ones. This is at least 3 to 4 times larger than that. And you'll see why. When we look at the quantiles, there's a little bit of evidence that it wasn't quite in equilibrium yet at the beginning as far as nu is concerned. But the autocorrelation function is much worse than any of the other parameters. This is behaving like, and I'll define this term next time, an autoregressive time series of order 1 with a first order autocorrelation of about 0.8, plus 0.8. And so that's not mixing well at all. But even so, with only 100,000 draws, we've got things down to a Monte Carlo, a standard error of about 0.01. So can I report the 3? Well, yes. Can I report the 3.6? Well, yes. Can I report the 3.626? Definitely. Well, probably no, because we're already down there. Oh, it's kind of 3.62, give or take about 0.01. So that's the sort of accuracy we've got so far. If you wanted 3 significant figures on this for some reason, you'd have to go out a lot more than 100,000 draws, because this autocorrelation function is showing rather poor mixing. This is the parameter that governs the shape of the. It doesn't have anything to do with the any of the things like the the proposal distribution, standard deviation. All that stuff is under the hood in WinBugs. It's done all the decisions for you about the proposal distributions. And in fact, if you wanted to intervene and get it to do something else, it's actually rather hard to do that. But I don't recommend that you do. They wrote the code pretty well, and their default Metropolis Hastings sampler is pretty good. Now, what about the predictive? This is interesting. Let's see how that goes. Its trace looks like that. That actually, strangely enough, is the trace of an IID white noise story. Because look, the autocorrelation function for the predictive is white noise, as I promised you before, because we're making independent draws from that T distribution with those parameters. But the history shows that in the T family, with only about 3 degrees of freedom, using the location and scale parameters that we have here, if you're really going to take 100,000 draws, every now and then you're going to get one that's very wild in relation to how the data actually behaved. The biggest data value itself was only about 420 or 30, something like that. And yet one out of every 100,000 of these draws gets a value for the next observation on the order of 1,000. And so maybe that's a prediction about what would have happened with the NB10 measuring process if they had gotten more than 100 observations. I'm not too bothered by that, though. It hardly ever goes out that far. It doesn't really call into question the T model that much. But my predictive now is it's approximately, it looks like some kind of witch's spike, but that's just because it's got to cover its butt with respect to all the range of the values it saw. Again, you ought to be able to tell it to plot these pictures from and to on the horizontal axis, but I don't know how to do that in WinBugs. And if we did that, we'd see it was more more tightly concentrated in the region of interest to us. But this again will show us that prediction is harder than inference, because look, here's the stats for mu, and there's the stats for y dot nu. And I'll go ahead and make them both a little bigger. Naturally enough, both the posterior mean, because the T model is symmetric about mu, both the posterior mean of mu and of y dot nu are the same. They're both equal to 4 or 4.3. But which of those quantities, when thought of as unknown or uncertain quantities, has more uncertainty attached to it? Mu or y dot nu? Vastly more, and that's because of that thing we talked about in the Poisson case study. There's two components. There's only one component of uncertainty here, namely how uncertain you are about mu. There's two components of uncertainty hidden in here. There's uncertainty about mu, and then there's uncertainty. In fact, there's uncertainty about the whole parameter vector, and then there's uncertainty about the future t value given those parameter values. And so naturally, this is going to be a lot bigger than that was before. So your predictive intervals are always much wider than your inferential intervals for parameters that correspond to the same mean. And that's as it has to be. Yes, please. Winbugs is doing some kind of MCMC under the hood that is actually pretty hard to figure out. It's probably doing, it probably has worked out that if we knew what nu was, no, not even that. I was going to say if we knew what nu was, things would be conditionally conjugate for some parts of the other part of the model. And if so, it's doing Gibbs sampling on the things that it can. Its general rule is to try to give sample parameters that it can figure out the full conditional for, and then go ahead and do Metropolis Hastings on the other parameters. But again, if you tried to ask this code right now to print out for you a little summary of exactly how it did the Metropolis Hastings sampling, it's hard to get it to do that. There's some kind of big diagnostic dump that you can, there's a button you can press that has lots of information in it that only the Winbugs developers can read, and somewhere in that code it says what it's doing. So this has been an example of how to use Winbugs in a relatively simple problem. However, the transition from the simpler model we talked about that we were able to analyze in conjugate form to this model here, in terms of difficulty of doing the analysis, is actually dramatic, and it's all hidden by how easy it was to do this. If you wanted to fit a Gaussian model to this data, then it would look like this. Let's go ahead and just do this freelancing right here in real time. I can copy this model over here and make it into a simpler Gaussian model for the data. By doing what? You guys can help me. What should I do? The first most important part of this stuff is always the sampling distribution. So what should I do? Go in here and edit what? Instead of dt, what should it be now? dnorm. And what are the parameters of a normal? The mean and the precision in Winbugs' world. So I just edit out the nu. And that means I edit out the prior for nu. And look, I can use the same priors for mu and tau as I did before. And the sigma still makes sense. But now what I need to do to change the y dot nu, it becomes dnorm, and I get rid of the nu. And in about 15 seconds, I have the model for the normal. Or to put it the other way around, this is a model that actually we can analyze in closed form, but Winbugs knows how to do it as well. And that's a model that's up until about 1990, all Bayesians knew how to fit this with paper and pen. This other model here, no one knew how to fit with paper and pen. It's actually quite difficult to do the maximum likelihood analysis in this model. And yet, the level of effort on our part in going from this thing called Untitled 5 to this one called Untitled 1 is absolutely trivial. We had to do hardly anything to move from a relatively easy model to fit in Bayesian terms to a relatively complicated model to fit. And the result is that you don't have to focus only on models that you know how to fit anymore. You can begin focusing on models that might actually have a chance of actually fitting the data instead, and then not worry about these issues about how to actually get parameter estimates, because all that stuff is taken care of for you by the inference engine here. So Well, do you mean am I going to? Oh, yeah. Let's find out how things mix. First, I have an immediate regret. I should have. I wanted to show you the posterior for mu in this model here. So quickly, I'm going to go ahead and get that again. So I'll go model specification. I'll bring this guy down again and check it. It'll say replace the old one. OK, fine. Bring the data in, compile, bring the inits in, load them in, and gen inits, all the stuff that I showed you before. Model, again, update. I'll do the same burn-in as before. And now inference samples. Now let's just say we want mu. That's the only thing I'm really interested in is mu. So I'll set that and get my 100,000 observations refreshing every 10,000. And it'll take that same 14 seconds it did before. So this model we already know about. Yes. And I'm about to show you how it goes. And so now let's look at mu and get the stats. So according to the T model, that's what we believe we know. And I'll also show you the autocorrelation function. And I'll also show you the marginal density. So those are all from the T model. Now I'm going to kill off the monitor tool and the update tool. And I'm going to park these guys down below. And I'm going to park this model here also and try to bring up untitled 5. Oops, that's not what I want. I want this guy. No, that's not what I want either. Wow, where did it go? I see. I wanted this guy. There we go. Okay, so that's, pardon? Y.new is our draw from the predictive distribution. This is all going to work fine. This model's good now. The same data set can be used, except I have to have a new initial values because it talks about new, and the other one doesn't know. This new model doesn't even know what that is. So I'll create a new little inits window here, copy this stuff into it. And get rid of the new. And minimize this guy because it's not the right one. And now let's fit the new model. So I'll hit go model specification again. It will now replace the old one, fine with me. And I'll read in the data and compile. And I'll bring in these guys and hit load inits. Again, it's uninitialized because of the y.new. I'll gen inits and everything's ready. Now I'll go ahead and do the same sort of. Now notice it's not adapting anymore because this is a conjugate prior. It's just going to fly really fast on the sampling now, and I'll get the samples. And just again, for simplicity, I'll only sample the node mu and ask it for 100,000 and refresh every 10,000. Watch how fast this goes. 100,000 updates took 0 seconds. So it actually did conjugate. It actually did conjugate updating here, and it can do that. It isn't even MCMC in this model. This is Monte Carlo, not Markov chain Monte Carlo in this model. But now let's look it up. First, let me unveil the other guys. So here was the kernel density before and the autocorrelation function before. Now let's put all these other guys away because they're just getting in our way, aren't they? And the node statistics before. Restore, yes. So that's the story under the T model. Now let's compare each of those things one by one. So here's mu, and the marginal posterior looks like that. And they're hard to compare because they're on different horizontal scales, but let's see if we can do a rough comparison. No, it's actually hard to compare, isn't it? Because they're on different scales. Or maybe not so badly because the scale is still 2, but actually no, it's not quite comparable because 2 is a different width. But now let me show you the autocorrelation function. It has to be white noise now because we're doing we're doing Monte Carlo, not Markov chain Monte Carlo. But now let's check out the stats. Under the Gaussian model, the answer is, well, I think that NB10 weighs about 404.6, not 404.3. And moreover, under the Gaussian model, my uncertainty is much larger. Look at that. The uncertainty band in the T model is driven by a standard deviation of about 0.47, and for the Gaussian model, more like 0.65. This is a part of a general pattern. The Gaussian turns out to be a conservative model for data when you're trying to learn about location parameters, center of distributions. It's actually, we talked about Fisher information the other day about maximum likelihood, I think, right? So it's actually, the Gaussian is the distribution of all symmetric unimodal distributions on the real line. It's the distribution that minimizes Fisher information. So what that means is you're getting the least amount of information possible about the center of symmetry if you assume the Gaussian distribution, which is a kind of ironic and interesting thing. From the beginning of statistics until fairly recently, everybody always assumed normal curves in every direction because it was the only distribution they could compute with. And strangely enough, if the world really is symmetric and unimodal, these people have had a built-in robustness factor in all of their inferences because the normal distribution is not allowing them to learn about the center of symmetry at a rate that's as fast as what's really there for them if the data really weren't normal. So it's a kind of historical accident in which there's a sort of built-in robustness happening here. I'll talk more later on about the implications of getting an uncertainty band that's much narrower in the T model, why that happens, and how we can compare one model with another and see which one does a better job of describing the data. So to wrap up today, we have a couple procedural things. First of all is to note that next time we are not meeting here in this room. We are meeting, where was it? That was that. Let's go back to the web page and look at, next time we are meeting in Bluewater, which is off of Charleston Road. And if you look and see what that involves and zoom out a little bit, those of us who are used to getting off at Rengsdorf, we can still get off at Rengsdorf, I guess, or we could get off at Shoreline. That would be easier, I guess, if we're coming from the south. So get off at Shoreline and come up to Charleston and go to the right, and there you'll be. And the website says you want to look for building what? Building 1220. And so find building 1220. There should be somebody there, just like usual, opening the door for you, and they'll help you get to the meeting room called Bluewater. And what was the other thing I wanted to say? Some people are interested in using WinBugs in the pharmaceutical industry. There's a whole user group. If you go to your favorite browser and type in WinBugs pharmaceutical industry, you'll find all manner of useful things. If you go to the comprehensive R network, archive network, and type in Markov chain Monte Carlo, you'll find that there's actually 5 to 10 different MCMC packages that various people have written in R to do MCMC that are competitors to the WinBug story. So if you prefer to do your MCMC work in R, you can try some of these things. As a warning, I'll tell you that the interface, the user interface, is nowhere near as good in these R functions as it is in WinBugs. They paid quite a lot of attention to that. So another reminder about this webinar next Thursday about approximate Bayesian computation. It arrives in our course too early for us to really understand what's going on here, but no harm in having it now. And I may refer back to the slides from it later on. And so thanks for coming, and I'll see you 1 week again from today. Yes, my pleasure. If you have your form, your survey form filled out, it'd be great to add it to the pile up here. And otherwise,